So what do you remember from grade 9 chemistry? That's what we're going to be talking about today. Absolutely nothing? Blank slate? Okay. Well, you should have learned about atoms, elements, and their composition, subatomic particles. Those were the big things. Anyone here completely bewildered by that? They're like, what's an atom? What's a periodic table? Such a talkative bunch, right on. So let's start with just a really basic question. What is chemistry? What is chemistry? What do you think? What's everything made up of?
Atoms.
Atoms. I would say everything's made up of matter, and matter is composed of atoms, right? Now, chemistry is the study of matter. All matter is composed of atoms. Atoms are the smallest unit of matter. If I had a giant block of gold and I kept chopping it up until I got to the smallest particle, what would it be? An atom of gold, right? So your elements on the periodic table are the building blocks of all matter. Interesting little discussion. Where does the atoms on your periodic table come from, the different elements? Where did they come from? Were they all just here when the universe started? The only element present when the universe first started out was actually hydrogen. So how did all the other elements get made? How did all those other elements get made? Did you guys do astronomy in grade 9? You guys skipped astronomy?
Yeah.
Okay, this explains this. So I'll give you a really minor astronomy lesson. So, in the core of a star, you have a fusion reaction going on, right? Hydrogens are coming together to form helium. Heliums are coming together and fusing to form heavier elements, and so on and so forth, until you get all the way to iron. Iron's kind of like when your campfire's burned out and all you have is ash left. There's no more fusion energy generated to hold that star up. It's kind of out of fuel. So then it will, if it's a large enough star, it will collapse in under its own weight, go supernova, and all of the other elements after iron are formed at that time. So if you are, for example, wearing any piece of jewelry, see a couple in the room. If you're wearing a piece of gold, for example, if you look at where's gold on the periodic table, try to find it right now. What number is it?
79.
79. Yeah, it's AU. Gold is AU 79. So that is way further down than iron. The gold you are wearing was actually formed in the core of a giant star as it went supernova, probably the star that made up our solar system about 4.6 billion years ago. So, it's going to sound cheesy, Neil deGrasse Tyson says it all the time, we are made of star stuff. So all of the elements on your periodic table were formed in the core of a star other than hydrogen. Now, the atom is the smallest unit of matter, and it is indivisible. If you break apart the atom, it is no longer matter. It is no longer matter. Now, what determines what element you have? Yep. One of them? It is actually the number of protons determines what element you have, yeah. Electrons are going to be the big focus of this year, though, because electrons determine how that element bonds, how reactive it is, how many other partners it needs when it bonds. So electrons will be super important, but for today, we're going to be focusing on neutral atoms. Atoms that have what? If it's neutral, it has the same number of?
Protons and.
Oh, good. You guys do remember something. You were lying before. Same number of protons and electrons. So, just like this house here is made up of Legos, all matter is composed of these basic building blocks. Now, in your atom, there are protons, neutrons, and electrons. Where do we find the protons and neutrons?
In the inside.
In the inside, which we call the nucleus, right? The center of the atom. Anybody know what the function of neutrons are? Let's think back to grade 9 electricity for a moment here. Protons have what charge on them?
Positive.
Positive charge. And what do like charges do? If I have two of the same charge, what are they going to do? They're going to repel. I'm going to make reference to grade 9 electricity a lot because a lot of the understanding of bonding comes down to this concept. They repel. So neutrons are there to kind of spread out that charge. Neutrons are a very important part of your nucleus because those protons would want to repel each other. Electrons have what charge? They have negative. And you find them where? Yeah, some of you may have heard them called orbitals or electron rings, I heard. However, we kind of lied to you in grade 9. We're going to lie to you again this year. This is not what an atom looks like, right? What do you guys think an atom looks like? Do you think it looks more like this? No? I would say no, this is also a horrible depiction of an atom. If I were to look at hydrogen, for example, and look at, take a bunch of photos of it. So if I had a camera and I was just snapping photos over and over and over again, this is what I would see. So here is the single proton that makes up the nucleus of hydrogen. And this here is that single electron. So we snapped a ton of photos, this is kind of what it would look like. Now we can see the electron kind of is found in this area more often than not, but look, sometimes it's found outside of it. The proton is kind of always found in this area, but not all the time. So these electron probability clouds, proton probability clouds, this is a much better depiction of an atom. But why don't we use things like this? Why do we use models like this or Bohr models that you would have learned last year?
It is more simple.
Exactly, right? It's more simple and it's easier for us to understand a lot of the concepts we're going to talk about. So a lot of the models that we're going to use in this class, yeah, they're complete lies, right? An atom's actually mostly empty space. It's like, I forgot, it's like 99.999999996% empty space. So if I wanted to draw an accurate depiction of an atom, I would have like my nucleus here on the whiteboard, and then I'd have to go to like King's Park to start to draw the electrons, right? So clearly we're not going to do that. So for practicality's sake, we do these models because it allows us to explore concepts in regards to bonding and other things and make it a lot easier to understand. So just know though that we're feeding you a bit of a lie there. How small is an atom? What do you think? How small is an atom?
Too small to matter.
Yeah, very hard. I think there was a picture of an atom taken for the first time not too long ago. More the shadow of an atom, but still. They are extremely, extremely, extremely small. How small is a cell? You guys would have learned a little bit about cells in your education. How small is a cell? You can see it under the microscope, right? But you're composed of an insane number of cells. In a single cell of your body, there is more atoms than there are stars in the Milky Way galaxy. Right? So atoms are extremely, extremely small. Alright, so let's go through this very quickly. You guys nailed it. What charge does a proton have? Protons are positive. Electrons were?
Negative.
They were negative. And neutrons, do they have a charge?
No.
No, there's no charge, right? And if you look on your sheets, I think most of you figured it out. Good morning. Most of you have figured it out. There is some blanks to fill in. Now keep in mind you will be getting booklets, I just have not got the printing yet today. Where do we find protons? Nucleus. Where do you find neutrons in the nucleus? Where do you find electrons?
The outer rings.
Yeah, electron shells or orbitals. I'll be calling them orbitals. They orbit outside of the nucleus. This is more of a tricky question here. What is the mass of a proton? Sorry? Sure. What is the mass of a proton? Yeah, it's 1. 1 what? Do you guys remember the units? You guys ever heard of AMUs?
Yeah.
Atomic mass units? So protons weigh 1 AMU. What do neutrons weigh? And I'm lying to you a little bit. It's 1.0 some crazy decimal number, but it's pretty much 1. What about neutrons? About the same as a proton. They weigh about 1, right? Now for the tricky one. How much do electrons weigh?
Almost nothing.
Almost nothing's a great answer. It's 1/1837th of an AMU. So you would need 1,837 of them in order to equate to the mass of a single proton or a single neutron. So when we're doing our calculations, we don't really consider the mass of electrons when we're figuring out like the number of neutrons, for example. Why is that? Because you said they what, sorry?
It's pretty much nothing.
It's pretty much nothing. That's an important fact to remember. It's pretty much nothing, which is why when we talk about the mass of an atom, it's mainly made up of what part of your atom? The protons and neutrons, your nucleus, right? The mass of your atom is your nucleus. Now, your number of protons is your atomic number. If I were to change the number of protons, you have a different element. Tell me, what element has 17 protons?
Chlorine.
17. Chlorine, yeah, same family, you just looked one above it. It'd be chlorine. Now, if we removed one proton, what element is it now? It's going to be what? If I take away one proton,
Sulfur.
it's going to be sulfur, right? So the protons determine what number you have, what atomic number. Your neutrons, how do you figure that out? Do you guys remember? Yeah?
You subtract the number of protons from the weight. So that's
Excellent. Perfect. Yeah. And we're going to do a couple examples, and that's kind of the tricky thing kids often don't remember. And then lastly, in a neutral atom, with this neutral meaning the same number of positives and negatives, clearly your number of electrons will be equal to your atomic number as well, right? Because if it's neutral, you got the same number of protons and electrons. Okay. What are periods on your periodic table? What are the periods on your periodic table? Are they the left to rights or the up and downs? Sorry? Is it the left and rights or is it the up and downs? Sorry. I'm hearing like a bunch of mumbling here.
The up and down.
It's not the up and downs. It's the left and rights, right? So your periods are going to be the left to rights. Now, it's the horizontal rows. And if we look, our first period here, how many elements are in it? Now there's two, there's hydrogen and there's helium. What about in our second period? How many elements are in that one? Sorry? There's 8. What about in our third? There's 8 yet again. Now, when we start drawing Bohr diagrams, you'll see right away why we break them up into periods like we do, right? This is an awful weird structure. Why is there 2 then 8 then 8? Well, it has to do with the number of shells, the energy level of your electrons. So, the period number tells you the number of shells, the number of electron orbitals. Now, unlike the other thing we're going to be talking about, periods, they do not have similar properties, the elements found within them. If we look at the up and downs, you guys remember what these are called? The different columns. The groups, also known as, let me give you a hint. Who here has brothers and sisters at home? Pretty much everyone. Now, would you say that you're identical to your brother and sister? No, unless you literally have the exact same DNA, you're identical twins. You're not going to be the same, but you have a lot in common with your brother and sister. I would say yes. Lots of students are like, no, my brother's not even close to me, but you do, right? You have a lot of things in common. So the up and downs, the columns, these are families. And these elements do share physical and chemical properties. Now, you don't have to worry about writing this down. You will have a notes booklet. We are going to be talking about this again in 2 days, so don't stress too much about it. Right now, I just want you to focus on the lesson. Now, we will be talking about Bohr diagrams on Monday, so please tune in. Probably will have the instructions and the video posted by around 2 o'clock-ish. Okay? But now let's explore one individual atom. Let's explore what you would have learned in grade 9. So in grade 9, you would have learned how to calculate the number of protons, electrons, and neutrons based on what you see on your periodic table. So let's use that example of chlorine again. Now, chlorine has an atomic symbol, Cl. Now, the atomic symbols, it is very important you become familiar with them, because when we are writing out the recipes in chemistry, we're going to be using the symbols. Why don't we use the full names? Because chemists are lazy. We don't want to have the full name. That'd be ridiculous. So we're going to use the atomic symbols for that. Now you should see a number above the atomic symbol. What is this number here? Yeah, that is your atomic number. And remember, the atomic number tells you what? Yeah, it tells you the number of protons. In fact, the only reason it's chlorine is the number of protons, right? And the number of protons determines what that element is. So this will be representative of the number of protons. Now, my shorthand for protons is peoples. In a neutral atom, what else is the atomic number representative of? Neutral means the same number of positives and negatives. So this will also be equal to what?
Number of neutrons.
Not the number of neutrons. Yeah, electrons. Yeah. So this will be equal to the number of electrons, which I use E negative like that as my shorthand, but only in a neutral atom. only in a neutral atom. That is a very important distinction. Probably one that you didn't talk about at all last year. Atoms are going to form bonds based on the number of electrons. And the first type we're learning about, we're going to be losing electrons and we're going to be gaining electrons. So that number of electrons is not always going to be equal to the atomic number. Last up, you're going to see a number below here. What is that number?
Mass.
It's your mass, and for chlorine it is 35.45. So this is going to be my atomic mass. That is going to be my atomic mass. Now we talked about this. How much do electrons weigh?
The
1/1837th. We don't need to worry about them, right? They weigh almost nothing. So really the mass of our atom, we're going to ignore the electrons. So what part of our atom then makes up the mass of that atom? The nucleus. Excellent. So really, when we're saying atomic mass, this is really the mass of our nucleus. Right? Because electrons weigh almost nothing, so it's effectively the mass of our nucleus. Now, if I wanted to find the number of neutrons in chlorine, how would I do that?
mass number subtract.
Yeah. So it's going to be your number of neutrons, which my shorthand for that is like that. My number of neutrons is going to be equal to our atomic mass minus our atomic number. Another way of saying this is like the mass of our nucleus, take away the number of protons. Because remember, our nucleus makes up the mass of our atom. And what is our nucleus? It's protons and neutrons. We take away the protons, we are left with the neutrons. Does that make sense? Okay. So, how many protons does chlorine have? How many protons does chlorine have?
35? Well, no.
No, protons. Protons. So it's based on our atomic number. So how many protons?
17.
Has 17. Right? So for chlorine, we have 17 protons. How many electrons do we have in a neutral atom of chlorine? 17 yet again. Right? Our positives and negatives equal out. That's why it's neutral, uncharged. So there'd be 17. Now, what about our number of neutrons? This is a little tricky here, because we have this really awkward 0.45, right? What were you taught to do last year? Round to the nearest whole number. So if it's 0.5 or greater, you should round up, and if it's less than 0.5, you should round down. So are we going to round this up or down? We're going to round it down, right? Because 35.45, 0.45 is less than 0.5. Therefore, we round down. So that is going to be 35 minus, what is our number of protons? Minus 17 to give us 18 neutrons. Now let me ask you a slightly different question, one that you may not have gotten last year. Where does this 0.45 come from? Think about it. How much does a proton weigh? What's its mass? 1 AMU. What about a neutron? Same thing, 1 AMU. And electrons weigh, what's the mass of electrons? Almost nothing. Just keep it simple, almost nothing, right? Not enough to account for this 0.45. So where the heck did that 0.45 come from? Yeah?
The atom can, there's like atoms that have like 35 neutrons and like 36 and like 37, and the most common is 35.
Not 35, you're exactly right, but not 35 neutrons, you're talking about the mass. Right? There's chlorine atoms that weigh 35, and there's chlorine atoms that weigh 37 AMUs, but 35 is the most common. For those of you that didn't pick up on that, what he's saying is different atoms can have different masses. But keep in mind, what can you not change in an atom? Because it'll change what it is. Protons. So what must be changing then? The neutrons. Excellent. Man, you guys are smart. So if we look at this through that lens, where does this 0.45 come from? Well, your periodic table is meant to represent nature. So we take the average mass of what we would find in nature, and that's the number you see. So this is actually an average. You don't find atoms of chlorine that weigh 35.45. That's not a thing. What you do find is you find atoms of chlorine that weigh, instead, 35 AMUs. In fact, that's the most common form of chlorine you find, is chlorine 35. Now, you sometimes also see atoms of chlorine that weigh 37. These are called isotopes, and you'll learn a lot more about them next year in grade 11 chemistry. But different elements have different stable isotopes, differing numbers of neutrons that allow those atoms to be stable. So in this case, chlorine has two main isotopes, chlorine 35 and chlorine 37. So how many neutrons does this one have? We just did. How many protons did it have? 17. How many electrons? 17. How many neutrons did we say chlorine 35 had? Remember, we rounded it down to 35. 18. Well, if that's the case, what's changed here? We can't change the number of protons, it's still 17. And our electrons are going to be the same in a neutral atom, but how many neutrons does this chlorine atom have? It has 20. 37 minus 17 gives us 20. So when you see those decimal numbers on your periodic table, it's because it's an average of what you would find in nature. And in nature, we find something like, I want to say it's something like 70, it's approximately 75-ish percent this, and approximately 25-ish percent this. Very approximately. Does that make sense? So if I took a scoop out of some big bucket of chlorine, you would expect to find about 75% this isotope. So 75% of your atoms would have 18 neutrons, and about 25% of your atoms would have 20 neutrons. Everyone following me? Yes? I do. So isotopes are not something we're going to talk a lot of in this class, but on your practice sheets you got today, there are some little tricky questions where you might be like, Mr. Salt, there's no element on here that has an atomic mass of 2. Well, you got to think about that for a second. How many neutrons does it say it has? So be a little careful when you're looking over there. It's going to trip you up a little bit. So think about, well, different atoms can have different stable isotopes, different numbers of neutrons. Let's do a couple examples just so you guys know what you're doing. So someone give me an element, something greater than, let's say, atomic number 26. Iodine? Sure, we can do iodine. Now if we look at iodine, right, here's iodine. What's the atomic number? Sorry? 53, everyone agrees? Quiet group. Yeah, 53. Now, what is the mass you see on your periodic tables? What does it say there? 126.9 AMUs. So how many protons are in iodine? What is the number of protons? Yeah, excellent. It's 53, right? The number of protons tells you what element it is. Most people think the atomic number tells you the number of protons. It's actually the opposite, right? Your element is defined by the number of protons, which gives you the atomic number. So it is 53 protons. How many electrons do we have? The same, right? Right now we're just dealing with neutral atoms. Same number of positives, same number of negatives. So we have 53. And then lastly, what about my number of neutrons? How do I solve that again? It's my atomic mass subtract my atomic number. Therefore, it's going to be 120, round this up or down? 127 minus 53, which gives you? 74. Mental math in the morning is tough. So our number of neutrons is 74. Okay, would you guys like me to do one more example? Oh, you guys are going to have to learn to speak. We'll do one more quick example then. So someone give me another element. I'm going to pick on somebody here. Give me another element. Sulfur, sure, sounds good to me. Sulfur, what is the atomic number of sulfur? 16? Does everyone agree? Yes? What is the mass of sulfur? 32.7. Is it 07 or 7?
07.
There we go, that's what I thought. 32.07. So what is our number of protons?
16.
That's right, it is the atomic number, so it's 16. What is our number of electrons? 16 yet again. And what is our number of neutrons? It's not 32, it's our, 32 is everything, right? So that's going to be our nucleus. That's our protons plus neutrons. We need to remove our protons, therefore we have 32 minus 16 is 16. So it's our mass of our nucleus, 32, minus taking out those protons and being left with those 16 neutrons.